take one point and we'll just take one unstable direction as an example. In your state space, you have a point Q. It's in many dimensions. And from it, there's an eigenvector. Tangent space is the same dimension as space. So if this is a 37-dimensional space, this is a 37-dimensional vector. I draw it, it's not one dimensional, it's 37, it's the same dimension. Then what you do is you play with it and get some sense of how far do you have to go before the nonlinearity of system becomes important. Your equations tend to be nonlinear, and what it'll mean is that if I take some point close to this and I let systems iterate it, remember in the Poincaré section, so it'll come back, and if you're close to fixed point, it'll come close to fixed point because it's unstable every time it'll come out a little bit further. And if you notice that there's some curvature in the space, it means nonlinearity has kicked in. So I don't have a good measure. You have to check it in every system, but typically your equations are good to maybe, a computer works on 10 digits, but the important objects of size 1. So if you take something sufficiently close, it'll march first linearly and then it'll start marching a set of points going there. Now if you take another point in between, by topology it's on a line, so it has to stay there. If you take 100 points, then it'll look like an interval. And if you do it so cleverly that the first point of this interval maps at the end of the interval in one iteration, so one Poincaré map of xn lands you here at xn plus 1, then what will happen, that the entire interval will get mapped onto itself. So the next time it will also be an interval, which to naked eye will look as a line because it has lots of points in it. But it'll be stretched because the distances are multiplied. Anything along here is multiplied, any deviation, by the linear thing, by lambda. So if this is 10 to the minus 10 in distance, this thing will be your multiplier, expanding multiplier, I don't know which one, let's say the first one, the most expanding one, times your delta x. So there'll be a bigger interval. Then it'll become bigger still. Then it'll become bigger still. And pretty soon you'll start seeing this is actually 100 points because this is expanding itself. We are learning how to compute unstable manifold on a computer because there's no analytic formula for them ever. How do you actually see what unstable manifold is? An unstable manifold is a big volume because if there are 3 expanding directions, it's a 3-dimensional manifold. So for us, it's very hard to draw 3-dimensional things deforming. But we are so lucky that there is a natural coordinate system, which are the eigenvectors. So they work like the edges of the unstable. There's a volume. It's a parallelepiped in linear approximation. So if you start with a little parallelepiped, it's not a cube because angles are never orthogonal for these Jacobians. These are matrices that never have orthogonal frames. This probability 1, they just deform stuff. So you want to see how this parallelepiped is growing as you go further in time because all points are running away within the unstable manifold. And one way to do it is to figure out what the edges do. So now we are computing one of the edges. And that edge is a line. And that edge is a curved line in a space because close to equilibrium point, linear dynamics is good. We do not know that there are all kinds of other objects in a state space. But when you get a little bit further away, there's actually another point here, x cubed prime. And that one is going to mangle our flow because it has a different dynamics in its own neighborhood. So the unstable manifold will curve. And I'm telling you, you can, for your problem, you can actually draw a picture of it. See, this is a line. So even though you're in 46 dimensions and you have no visualization in 46 dimensions, you can draw a point and see what it looks like in any 2 or 3 coordinates that you chose. And you can also see what a line looks in any 3 coordinates. So even though you can't see these things, you can see quite a bit because it's 1 dimension, just a line. You know, it was a vector because you know, it's the edge of the thing. So here is my deformed surface. 1 vector points this way, 1 vector points this way. And now I'm just trying to figure out how this curved thing is going to look like here and how it will look like there. Yeah?
But this curve has no significance in the global picture.
Ah, good question. That's why we want it, because that's our invariant guide. That's you know, native guide from local neighborhood to the big global world. And it has significance because the invariant solution is invariant solutions in any coordinates, no matter how you do this. So no matter who does it where, they'll find the same invariant solution. There'll be a different position in their coordinates. It'll be same invariant solution.
So for that, you have to find the same point in the other coordinate.
Yeah, so in other coordinates, there'll be this point. In other coordinates, there'll be this vector, which is solution of the eigenvalue equation, because this matrix is defined in the coordinate set, and this vector is in given coordinates. So when we go to new coordinates, this vector will change to some other vector. And we discussed this very early in the beginning, that's called smooth conjugacy, how you get it. But the stretching rate is invariant. Stretching rate doesn't depend because the multipliers are properties only of dynamics and not of coordinate representation. Every solution has a different set of eigenvalues. Right now we are starting in a neighborhood where there is a unique set of eigenvalues, and we are using those to start sailing into the big world, but we are not doing it blindly. We are doing it on invariant curve, which will be invariant curve for everybody else as well, no matter how they, you know, stretch their world and plot it. They've all agreed that this is a continuation of the first unstable direction in neighborhood of this thing. Now, if this invariant curve goes into neighborhood of the second thing, or maybe even hits the second equilibrium, then no matter how I look at it, that's a topological property of the flow. So that's a very robust thing. So even though pictures of it might differ from person to person, the statement that the 2 neighborhoods are connected by an invariant curve will be an invariant statement. And the statement how I get from one to the other one will be also invariant, because this curve will be a unique curve. I will find the same you know, flight time between them, if you wish, because that's controlled by these eigenvalues. But now this curve goes off, and what this curve does, unstable manifold, so what's very important is to know, yeah, here you start, but you have to be wise enough to know when to stop. Because if you actually just keep using your dynamical system and iterating, this turns out to be a curve like any other curve. In long time, usually it's an ergodic trajectory. And it's doing what every ergodic trajectory does, it's exploring the neighborhood, it goes all over the place. So if you don't stop someplace, you will just start filling out whole state space with this curve. And you will not be any wiser than just running any random point. Yes? Locally, we have very clear definition, but they have unique continuation. There are no 3 curves. So strategies that we have figured out linearized neighborhood of this point, call it xq, linearized neighborhood of some periodic point. This is all in Poincare sections, so they're all morally fixed points. And another one, x p1, p2, and we want to put this picture together. And I'm now, so locally we have very good maps. Linearized tangent space is really good. But globally, what are we going to do? Now I'm telling you, there is a smart way to do this. You put lots of little charts and put the shortest connections between them, and then you control everything. Periodic orbit, when reduced to Poincare section, is a set of periodic points. And each periodic point is a fixed point of the nth iterate of the map. So if you understand how to analyze one fixed point, the same methodology works for all periodic orbits. Because they're just different maps. But once you figure it out, you know how to do it for all. So that's the idea. And that's why we had to go slice and cut, etc. Once we have reduced dynamics to just the dynamics of a fixed point, then we have machinery that describes all this invariance, even though there might be tora, etc. in a full state space. We will only compute eigenvalues of invariant objects, which are stationary, like periodic points. They're stationary under nth iterate of the, and this we will only use to have topologically invariant way of connecting the neighborhoods. So there is no particular meaning. If I compute Jacobian on this trajectory for some finite time, it'll have its vectors and eigenvectors. But they don't have any invariant meaning, because the only thing that have invariant meaning are the eigenvectors and eigenvalues computed on compact sets on periodic orbits or equilibria. That we showed first. So there are two things. There is one that we can do, which is on any compact set we can compute its eigenvalues and eigenvalues. Now if you're a mathematician, you can also do it in infinite time. So that's called Osseledek theory of Lyapunov exponents. So infinite time orbit is also an invariant orbit. It's just that it's in our gleaming mathematician's eye. We cannot control it at all. So we can't do any calculations on it. So we have a systematic procedure that we calculate longer and longer orbits. For them, we know what we are doing. First thing I want to say is that I just want to tell you, don't go very far. Just don't go very far, because whoever goes very far will find himself or herself running around the state space just like any other stupid trajectory. Any ergodic trajectory just runs around and you can't make sense of it. So all I want to say is that when you have a linear neighborhood, there is a way, so I put a picture actually in the book, there is a way of going out of the linear neighborhood and still have a nice neighborhood. It's just, like a cup. It's curved, but it's smooth and nice. But at some point that has to fail, because at some point you'll start hitting obstructions of other neighborhoods. And they are different, and they won't let you do this. They'll make you twirl and twist, etc. So what happens in the systems that I'm familiar with is you go for a while, and then you hit some kind of wall. So Rosler was a very good example. You went around, and then you discover that you're folding, and you can't go further. So these unimodal maps, for example, also. What happens with this trajectory when you plot it, you'll discover that you have hit some kind of wall and suddenly starts turning, and it does whatever it does onward. And now my advice is that you stop here. There are ways of defining the turning points well. I mean, basically, this is a curve and has curvature. And when it starts turning very quickly, it's like a mechanical object experiencing strong acceleration. It suddenly has to go back. And if you look forward in time, there are ways of defining it better. But basically, there is a part of the neighborhood that's nice neighborhood still, even though it's curved. And you can use these unstable manifolds to delineate that good neighborhood. So it means that you can make your chart bigger, So instead of just being a plane, it's some curved surface. And you can make the other chart bigger. So you started with infinitesimal information. So you had no idea how to go to your distant relatives or even enemies. But now you can experiment and you can see whether the neighborhoods intersect. Which means that if the neighborhoods are intersecting, then I might be able to make a nice connection and continue in the next neighborhood. So that's kind of general strategy of what you want to do. If you plot the same manifold in polar coordinates and Cartesian, it might look very different because something close to the z-axis might stretch. You know, it's like Mercator projection versus some other cartography projection. So visually they might stretch. But if there is a railroad from Moscow to Novosibirsk, it'll be there on every, even though it might look 1,000 miles longer or look very short depending on your projection, but topology will remain the same.